Welcome back to Larry's Classroom. We ended our last lesson by talking about square roots, and we're going to start today by talking about cube roots. Cube root is basically the inverse of raising a number or a variable to the third power. So we're going to give you some examples. We're going to put the radical sign here, and we'll put the 3 here to indicate we're doing cube roots. You probably recall that if we put no number there, that we're implying a 2 for a square root. Well, we say the cube root of 125 is equal to 5. And that is because 5 cubed, or 5 to the third power, 5 times 5 times 5 equals 125. So basically this cube root undoes the cubing operation. We're going to do another example here. We'll draw the radical sign, and we'll put the 3 in there to indicate we're doing a cube root. And we have 0.512. Now we have here a decimal fraction inside there. The cube root of that is equal to 0.8. And that is because 0.8 raised to the third power is equal to 0.512. I didn't bother to write out the 3 factors of 0.8, but you can see how that would work. And another thing you'll notice here, 0.8, 1 decimal place, we raise it to the third power, we end up with 3 decimal places in the result of multiplication, which we have here. And also we had 3 decimal places in the number we're finding the cube root. We took the cube root of it, that reduced it to 1 decimal place. It's useful to know some perfect cubes. So we're gonna write down some perfect cubes. We may use these. The cube root of 8 equals 2. In other words, 2 cubed equals 8. That's why we call it a perfect cube. And I'm going to keep I'm going to run these across I think I'll keep them right over here because we might use these in the next few examples. The cube root of 27 equals 3. Again, because 3 cubed, or 3 times 3 times 3 would equal 27. Cube root of 64 is equal to 4. Then you probably already guessed 4 times 4 times 4, or 4 cubed equals 64. The cube root of 125 equals 5, which we just did that one right there. And the cube root of 216 equals 6. In each case, 6 cubed equals 216. 5 cubed equals 125. 4 cubed equals 64. 3 cubed equals 27. 2 cubed equals 8. So the cube root is the inverse of the operation of raising to the third power, or cubing. And that is probably becoming fairly obvious to you by now. We're going to do a few examples here, and so we'll start with the cube root of 64 over 125. Now you remember our rules for powers and roots. These apply to cube roots as much as well as square roots, so we can separate this into the cube root of 64 divided by the cube root of 125. Now this is why we did these perfect cubes over here to help us do these problems. The cube root of 64, we see that's 4. So we can replace the numerator with 4. The denominator, the cube root of 125, which we've worked out here, we see that's 5. So this is equal to 4/5. And if you want to do the decimal fraction, that would be 0.8. So we're going to more formally define the cube root here. We've talked about it, and I think you probably understand it, but we're going to more formally define the cube root. Basically, the cube root of x cubed is equal to, we can take this exponent of 3 outside the whole thing, the cube root of x to the third equals x. So there's two ways to look at this. Here we have the cube root undoing the cube takes us over to the x. Here we've taken the exponent to the outside of the radical sign, put it in parentheses. Well, what is the cube root of x? If we multiply the cube root of x times the cube root of x times the cube root of x, we'll do that. It's going to be x. So we're going to say cube root of x times, I'm going to use a dot this time, the cube root of x times, we're going to use a dot again, cube root of x equals x. So basically if we reduce x to its cube root and then we use that result as a factor 3 times, it gets us back to x. So there's a couple of ways of looking at that. So basically the cube root is the inverse of the cube. We've seen that repeatedly. A couple more examples. The cube root of 8 cubed. Here we do the cube root of 8 cubed undoes the cubing, which basically equals 8. And we could say this is because the cube root of 8 raised to the third power equals 8. This is very much like our other examples we did, only we had perfect cubes. Now the cube root of 8, well, cube root of 8 is a perfect cube, isn't it? That was, what is 8 cubed? Yeah, 8 cubed would be a perfect cube. 8 times 8 would be, let's do that calculator. 8 times 8, 8 cubed. That's 512. So we'd be adding one more to the thing here. So we could also say this is the cube root of 512 equal 8. And that's because 8 cubed equals 512. So we've kind of displayed this in certain ways. The 8 cubed and 512 are the same number. 8 times 8, 64, times 8. Yeah, 64 times 8 is 512. So these two numbers are the same number, and because 8 times 8 times 8 equals 512, that says the cube root of 512 equals 8. And here we have just another way of writing 512. And here we've raised this cube root of 512 to the third power. We could also write this way. The cube root of 512 raised to the third power would equal 512. Well, that ain't right. The cube root, what am I trying to tell you there? Yeah, here's what it should be. The cube root, okay, we don't, yeah. We got third, we don't put third power here. So we just the cube root of 512 equals 8. We've already done that. We don't need to talk about it anymore. Cube root of 512 equals 8 because 8 cubed equals 512. But this guy here is the same as the cube root of 8 cubed equals 8. The cube root of 512 equals 8 because 8 cubed equals 512. Yeah. But 8 cubed is 512, so yeah. Anyway, cube root undoes cubing, just like square root undoes squaring. And if we were extended out, the fourth root would undo raising it to the fourth power. Add something else down here before we erase that. We can do a root as an exponent. Basically, we say that x raised to the n to the 1/nth power will equal x to the n times 1 over n, which will just equal, which is going to equal x. A couple ways you could look at that. We can, well, this is what we did here. We moved the exponent inside by multiplying n times n. Well, right here, big letters. N times 1 over n. But we can rewrite the n as n over 1. We can put any number over 1 to make it into a fraction, times 1 over n. Well, the n's cancel. We end up with 1 over 1, or 1. So we have basically this fractional exponent undoes this whole number exponent. But another thing we can see here, this undoes this. Well, this is basically equal to exponent 1 over 3. So we could say this way. We could say that the cube root of x is equal to x to the 1/3 power. So any root would equal the 1 over the root power times the variable on the inside here. So this exponent 1/3 is equivalent to the cube, the 3 on the radical sign. And this leads us to a way to do roots other than the ones you have. Depending on your calculator, you may or may not have a way to do a cube root or a fourth root. But you can, if you want to find the cube root of a number, say the number, we'll go with 512. You want to find the cube root of 512. Now, a lot of calculators have an exponent key. You can hit the exponent key, which often looks like a little up arrow thing there. You can raise that. You put a parentheses, 1 over 3, and that would give you the 8th that we got here. If you wanted the, let's just say we wanted the 6th root of 316. Say we wanted to find the 6th root of 316. We could type in 316, use the little exponentiation key on your calculator, put in parentheses 1 over 6, and let's do that on my calculator, see what we get here. This will probably be an irrational number with a bunch of decimal places, but we'll round it. 316. We'll hit the up arrow. I'm going to do a parentheses. I'm going to do 1 divided by 6, close the parentheses, and I get 2.6. I'm going to do approximately equal to 2.6098. We'll just, that's rounded to 4 decimal places. Now I'm going to take my calculator and I'm going to raise that back to 6. It should take me right back to 316, and it does. So there's a way you can get roots that are not on your calculator. And another thing it could be, depending on your calculator, you might have a 1 over x key, and you'd use that and just put the desired root in there. This particular calculator doesn't have that key, but yours may. Anyway, cube roots undo raising numbers to the 3rd power, just like square roots undo raising numbers to the 2nd power. We'll do a few more examples working. Now we're going to work with positive powers of 10. Say that we have this 4 times 10 squared. We're going to raise that to the third power. So let's rewrite this, put in parentheses. 4 is 4 to the first, right? Times 10 squared. And the third power on the outside. Well, basically, when you have an exponent on the outside of a parentheses, you can bring it inside by raising each factor to that power. So, well, 4 to the first times 3 is 4 to the 1 times 3. This exponent times that exponent gives us 4 cubed. And 10 to the 2 times 3 is 10 to the 6th. Now, 4 cubed. Well, the cube root of 64 was 4, so 4 cubed equals 64. So we can rewrite this. Oh, let's put the 10 in here. This is 10 to the 6th power. 64 times 10 to the 6th. So we've reevaluated this expression as a power of 10, a number times a power of 10. And I put the 4 to the first to demonstrate how you're bringing this exponent in, you're multiplying it by the exponent of every factor. We have 2 factors. We got a 4 and a 10 squared. The 3 times the exponent of the 4, which was 1, gave us a 4 cubed. The 3 times the exponent of the 10, which was squared, gives us a 10 to the 6th. So we're going to do a couple more of these. So powers and roots kind of go together. They undo each other. So that's why we're working these things all together here. 2 times 10, the whole quantity squared, everything in parentheses is squared. Now you could use your FOIL method and work this out, but I mean these are just, well, you wouldn't FOIL this, no, I'm wrong with that. But we're going to move the exponent inside. Well, we got a 2 to the first, raise the second power, gives us 2 squared. We got a 10 to the first, raise the second power, gives us 10 squared. So we do the multiplication here. We get 2 squared, 4 times 10 to the second power. So we've expressed this thing as simply a number and a power of 10. Do another one of these guys here. Roots, powers. The power really is a root, but it's a fractional. The root really is a power, but it's a fractional power. 1.62 times 10 cubed, quantity cubed. Well, 1.62, we bring the exponent in. The exponent is now 1, but multiply times 3, 1.62 cubed. Now we bring the exponent in for the other factor. The exponent is already 3. 3 times 3 gives 9. 10 to the 9th. Now, we're going to use approximate sign because when we cube this, we get a long decimal, but it comes out to approximately 1.62 cubed is approximately 4.25 times the 10 to the 9th. So there again, we've expressed this expression as a number and a power of 10. And if you wanted to write that out, we'll do this one for kicks. Approximately equal to 4, 2, 5, 0, 0, 0, 0. Basically, we move the decimal place to the right 9 places. Started here at point 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we ended up with, what do we got here? We got another, this is thousands, millions, 4,250,000,000, big number. This you can see is a little bit more compact way of dealing with it. And we only have 3 significant digits anyway, so we don't gain any more meaning here, but we have a more compact way of writing it by putting it as a power of 10. A couple more examples and probably be done for the day here. We're going to do, this is the square root this time. The square root, 1.96 times 10 to the fourth. And you remember this is equivalent to 1.96 times 10 to the fourth, the whole thing raised to the 1/4, which helps us in separating this. But we're going to separate down here. We have basically the square root of 1 to the 1/2 is the square root. 1.96 square root of that times 10 to the fourth. And we're going to put square root over that too. And now we're going to utilize the fact that the square root is the 1/2 power. Oh, excuse me, I've got a cube root here. What am I doing here? Well, we'll continue with this particular example, but basically 1.96, square root of 1.96. It gives 1.4, okay. Oh yeah, I'm in the right place here. 1.4. Then we're going to rewrite this square root of 10 as 10 to the fourth times to the 1/2 power, the whole thing. Yeah. I'm all fine here. I got on the wrong line on my notes for a minute here and got myself confused. We're good here. The 1.96, square root of that was this. We've rewritten this in that form. But now we're going to go down here. We're going to stick with the 1.4, which is all good and fine. We're going to move this exponent inside, 10 to the 4 times 1 over 2. Well, 4 times 1/2, this equals 1.4 times 4 times 1/2 is 2. 1.4 times 10 squared. So we took this thing, and we see that there. We could have run the 1/2 in there and said this was 1.96 to the 1/2 power times 10 to the fourth times 1/2 power, which is, that's where we got to here. It's just another way of rewriting the same problem. But the radical sign basically is the same as a fractional exponent. If it's a square root, it's a 1/2. If it was a cube root, it'd be a 1/3. If it was a fifth root, it would be a 1/5. And you could put any number up here for any root you want, but mostly we probably work in a lot of our electrical stuff with square roots and cube roots more than the higher level roots. But remember, this mathematics can be transferred to other things besides electrical stuff. We'll do one more like that. This is another cube. This one's going to be a cube root. 64 times 10 to the 9th. So we're going to separate them. Cube root being their factors or products, we can separate the root of products into the product of roots. This is products, the root of products. Here we got 64 times the cube root of 10 to the 9th. Here's a product, and this is the root of this product. Here is a root, and here's a root. This is the product of the roots. Separating them out into under separate radical signs doesn't change the value. It's a valid operation. So what do we got here? Well, the cube root of 64, we see here the cube root of 64 is 4. So we can replace that with a 4. Now, being we know that a cube root is like a 1/3 exponent, well, 1/3 times 9, well, we'll go ahead and write it out here. 10 to the 9th times 1/3. That's like 9 over 3. Basically becomes 4 times 10 to the 3rd. So we've taken this product under a radical sign, we reduce it to just a number and a power of 10. We use the fact that a cube root is a 1/3 exponent, that they're equivalent operations, to help us do that. We're going to do one more example here and probably call it a day. It kind of combines everything we've been doing. So we're going to go here. We got a radical sign. This is a square root because there's no number, but that means 2 times 10 to the 6th over 4 times 10 cubed squared. So we're going to do some separation here on the top. We're going to separate this root of a product into product of roots. So we're going to write here the square root of 16 times, we're going to use the square root of 10 to the 6th. We separate this root of products into product of roots. Now we're going to put this here exponent, we're going to bring it inside the parentheses. This is 4 to the first, so that becomes 4 squared. And this is 10 cubed, 10 to the third. We won't bring the 2 in there. That's 10 to the 2 times 3, or 10 to the 6th. We're slowly getting it more simple. So we're going to go one more step. We're going to replace the 16 with 4 times, well, 10 to the 6th. But remember, this is a square root, which is a 1/2 power. 10 to the, write that right here, 10 to the 6 times 1 over 2, which is the same as taking the square root, is equal to 10 cubed. 10 to the third power. We've taken this square root, which is a 1/2 power, times the 6th root. 1/2 times 6 gives us 3, so we got the 10 to the third power. So we simplified the top a little more. We're going to go ahead and let's go ahead and just write that out as 16 times 10 to the 6th. Now we're going to separate this into the numerical portion and the powers of 10 portion. Well, 4 over 16 times, we can separate these factors. 10 cubed over 10 to the 6th. And you can see this is the same because we multiply across the top, across the numerator. We have 4 times 10 cubed, which we have here. We multiply across the denominator. We have 16 times 10 to the 6th, which we have here. So it's easy enough to see if that's an equivalent operation. So we're going to simplify the 4 over 16. We're going to call it 1/4. So we've made that into a simpler fraction. Now we're going to convert this division into a multiplication. Remember how we did that? We went times 10 cubed, and we took this 10 to the 6th. When we moved it up to the numerator, it became 10 to the minus 6. So we're going to go down one more line. The 1/4 doesn't change. But how do we do this? When we're multiplying powers of 10 with different signs of exponents, we subtract the magnitudes and use the magnitude of the largest. So that's times 10 to the minus, because that's the sign of the one with the largest magnitude, 6 minus 3, and magnitude absolute value, same thing. Well, that equals 1/4 times 10. 6 minus 3 is 3. Use the sign of the largest absolute value or largest magnitude. So we have 1/4 times 10 to the negative third. Now we could rewrite that. We could go 1/4 is 0.25. 25 hundredths times 10 to the minus third. Now if we wanted to write that out as just a decimal without the power of 10, we'd have to move our decimal place 3 places to the left, because that's what the negative 3 indicates. So we'd end up with 0.00025. Our decimal place started right here. We'll move 1, 2, 3. So this expression simplified down to that version, 1/4 times 10 to the minus third. If we just use a fraction, we converted the fraction into a decimal fraction, 0.25 times 10 to the minus third. Then we wrote it out. We wrote the decimal out all the way, 0.00025, which is, what is that? That's tenths, hundredths, thousandths, 10 thousandths, 100 thousandths. That's 2,500 thousandths, right? Yeah. Or we could rewrite that this way if we wanted to, 25 over 1,000,000. So then this, and this are all equivalent ways of writing the same number, which we got from this fancy expression here. I think that covers what I wanted to talk about today. Thanks for coming. Be sure to like and subscribe. And as I keep trying to remind you, I would recommend you get some kind of math book and do practice problems to help reinforce these things that we're learning here. You know, any basic algebra book or something, you're going to, basic arithmetic leading up to algebra, which is where we're going soon, is to do some algebra, is going to have problems. We'll make use of these things we've been learning. So until the next time, keep on learning.